2 lectures back, we asked the question, how do we control for confounders and reverse causation? How do we, in other words, ideally establish causation? Well, today we're going to try to answer that question, if not perfectly, at least as best possible. And that is by talking about something called randomized controlled trials, or RCTs for short. I put the question mark here, is this a gold standard for causation? Because science is always evolving, and better might still come. But for now, RCTs are among the best possible techniques we have to establish causation in many circumstances. Let's get started. Remember that to find causation, you have to establish 2 things, besides the fact that the phenomena actually exist in the first place. Number 1, determinism. We achieve that by eliminating all confounders and chance. And number 2, directionality. We achieve that by eliminating the possibility of reverse causation. Now I want to remind us something in the big picture about association and causation. Remember, association does not prove causation. If someone says some phenomenon is, quote, linked to some other phenomenon, that doesn't really tell us anything other than that the two tend to change in coincidence with each other. It doesn't tell us causation. Conversely, however, causation usually conveys statistical association, except where there are negative confounders that obscure that relationship. So, statistical association is not causation. Causation usually does show us evidence of association. Why does a statistical association, to refresh ourselves, not prove causation? Well, number 1, there's the possibility of reverse causation. Number 2, positive confounders can obscure that relationship. Number 3, chance exists. We talked about chance a few lectures back when we talked about probability and frequencies. Events can be statistically significant, and yet they can still be chance. After all, the cutoff is set at a somewhat arbitrary 95% level, meaning 5% of the time we're wrong. Also, we have to remember that the converse is true. Absence of association statistically does not rule out the fact that a specific stimulus that we suspect to be the cause of a specific effect may in fact be true. Why would that be the case? Well, there are negative confounders. Remember the example of pregnancy being a negative confounder when we were looking at the relationship between the increased risk of thrombosis, clotting, and birth control pills. Second, just as is the case for the first instance, chance can also interfere with finding causation where there appears to be an absence of association. Association could be causal, that is, but it actually appears to be chance. As another point I want to bring up here, and we'll see again later in the class when we talk about risk communication, that it does not matter who is telling you that an association exists and that 2 events are linked with each other. It doesn't matter if it's a comedian. It doesn't matter if it's the nightly news. It doesn't matter if it's a scientist in a white coat. This is not a matter of authority or expertise or anything that's related to opinion. We are talking about science and knowledge here. And so ultimately, causation is not some sort of opinion, but rather it is grounded in fact and ultimately, ideally, experiment, as we will see later. Remember also, as we said in a previous lecture, that probability and statistics can help us to control for confounders. We talked about biases that we want to eliminate, as well as chance. There are some exceptions, and we talked about those on a previous day, but these are things that are often ruled out when we're looking at possible causation. One interesting point a student made to me once, and I just want to mention it as an aside here, and we'll come back to this issue in the future, is I had a student who once said to me, it seems to me there's no such thing as chance. You keep talking about chance when we're talking about causation. But at best, it seems to me a misnomer, he said. And at worst, it is a cop-out based more on superstition than science. When an experiment yields anomalous results, the logical scientific conclusion, he said, should be that there are variables affecting the outcome that have not been adequately controlled. The term chance, he says, probably should be replaced with a more descriptive term like uncontrolled variables or unknown confounders. I'm not going to quibble with this. This is sort of a philosophical view of how one looks at the world. And some people might say these are unknown confounders. Others might say there is a randomness to the universe that in fact is beyond explanation, and it's not simply confounders, but chance itself, that the universe perhaps rests on a pair of dice. One of the things I want to come back to here is what Mario Bunge, a famous philosopher, once said: the best grasp of reality is by causation, and that's not obtained by respecting fact and avoiding fiction, but by vexing fact and controlling fiction. We know causation is not perfect, but it's one of the best ways we have at looking at reality and trying to tease out what's going on. So, to get causal knowledge, we have to eliminate reverse causation and all confounders, things that are known, such as biases, and things that are unknown, chance, if you will. How do we do this? We haven't talked about that so far in this semester, and what I want to suggest today is that a bunch of crap actually led to this conclusion for science. There was a man named R.A. Fisher, who was a scientist in the 1923s, a statistician and a farmer by training. And he asked a question because a bunch of farmers were coming to him as a statistician saying, I want to know what sort of fertilizer to put on my crops in order to get maximum yields. And they were asking the question, does it really matter what kind of fertilizer I put on it, or can I just put any fertilizer on it? So Fisher was challenged with the possibility, a very real problem that was existing, of trying to maximize farmers' output. And so looking at this question, you can obviously see there are some confounders that would come up before we can automatically conclude that a fertilizer causes a better or worse yield on crops. Let's say we took a plot of land and we looked at it over time. One thing we might do in looking at that plot of land is to say, well, one year we'll plant without fertilizer, and the next year we'll plant with, in the same soil. And then we'll measure outputs one year over another. Do you see a confounder in that? Well, one obvious confounder that might come up would be weather. That is, from one year to the next, it might be a rainier or a drier year, or a more humid or a drier. And as such, yields of crops are obviously highly susceptible to the weather. And if we were to simply compare the relationship year over year, we might not actually get anything worthwhile scientifically to know because we have a confounder, weather. Okay, so we don't want to plant the same soil one year and then the next year because of this confounder. How do we run this experiment then? Well, one way to do this might be to plant soil crops right next to each other in the soil, one row next to the next, and then see how one row that we treat with fertilizer does and how the next row, which we leave untreated, does not. That seems logical, except soil has gradients in it. Soil has different qualities. Even in the same proximity to each other, within a few feet of each other, you can have different soil qualities. And the problem with that is, if we have plot drainage differences, or there's soil variation, and we plant one row with fertilizer and the next without, then the natural nutrients of the soil might be affecting the output and yield of crops, and we would attribute that incorrectly to the use of fertilizer or the non-use of it. In other words, plot drainage or soil variation could likewise be confounders. Well, that gives us a real conundrum, because how, after all, are we supposed to do this experiment if we can't do it one year after the next using the same soil, and we can't even do it in the same year using soil adjacent to itself? Fisher looked at this and said, what would we do by looking at the natural ways soil gradients run? He drew this map up to start with as an idea and said, what if I alternated the way that the soil were fertilized or not? For example, in one row I said fertilized, controlled, fertilized, controlled, fertilized, controlled, and I alternated my planting sequence. And in the next row I'd say controlled, fertilized, controlled, fertilized, controlled. He said that way I'm sort of alternating, and that might be a nice way to control if there's some runoff or something of that nature. Because after all, this would work if the natural gradient of the soil ran north-south, as my diagram shows it, or if the soil ran east-west. If water drained through and carried nutrients, then the soil would sort of have it equally dispersed as long as we alternated the use of fertilizer from one plot to the next. The problem is, what if the soil gradients run in a different direction and you don't know it? For example, what if instead of running north-south or east-west, the soil gradient runs from northwest to southeast? Then the fertilized soil would carry natural quality of crop gradients from northwest to southeast, and likewise that soil variation would carry with the water flow from control to control. In other words, you wouldn't have the control that you would wish for this experiment. There would be a confounder. Well, this creates a problem. So Fisher had to figure out a way to deal with this. And he did. He planted crops, in other words, randomly. And by doing that, he also randomly used fertilizer, not planting in any specific pattern, but randomized what row would receive fertilizer and what would not. So something like this, completely random, flip of the coin types of planting and planting with fertilizer. And by doing this, he basically rationalized that if a large number of plots could be involved at any given time, any natural land quality gradients or drainage would cancel itself out, and the only effect left to look at would be the effect of the manure as seen in the results. Well, if we draw this in a different way, just to sort of make a conceptual picture of this, here's the advantage of randomization. We can actually cancel out confounders. Look at the top part of this diagram and the bottom part. The only difference is the item D. In the bottom part, we have a whole bunch of different factors all contributing to the effect. Crop yield. We might have things like soil quality, nutrients of the soil, water, density, and so forth. A, B, C, E, F, G. These are all confounders, things we're not interested in studying as part of our experiment, but things that we want to hold constant regardless of whether we're treating with or without the fertilizer. What we're interested in seeing is what's the pure isolated effect of fertilizer in these cases. And that's achieved by manipulating this experiment so that in one crop, only the fertilizer is the variable of interest, and in the other, there is no fertilizer added. But in both circumstances, when we randomize treatment and randomize this in where it's planted in the soil, we cancel out statistically, and this is what Fisher discovered statistically, all the other soil confounders. So away goes A, B, C, E, F, and G as potential confounders, because both the manipulated soil, the one treated with manure, and the control soil, the one that was not, had the same confounders. And so we are left able to compare the isolated effect of just the manure on crop yield. This was a brilliant stroke of genius. And by doing this, Fisher effectively was able to isolate causation. This was a huge breakthrough. And what you're going to see in the next lecture is that in more recent experiments, Fisher's contribution has been carried out and is often used in circumstances where we take information for granted today as true. But ultimately underlying it is this RCT method that Fisher invented in 1923. We'll come back to this in the next class, looking at an example of heart attacks and aspirin to see how Fisher's RCT model was set up to test basic scientific knowledge in the medical field. Can you think of examples where an RCT might be useful for gaining knowledge for some causal question that you're looking at? Let's see. I'll see you on the chat boards.